Welcome to the Walton Pi. Today we're going to be talking about maximums and minimums. So maximums and minimums, well, those are pretty intuitive ideas. So a maximum's where you have your largest value and a minimum's where you have your smallest value. So let's just give us the mathematical language in order to describe them. So an absolute maximum of a function is a point f of c where f of c is greater than or equal to every other value of the function. So it is the absolute largest value of the function. The absolute minimum is the same sort of thing. It's f of c if f of c is less than or equal to f of x for every x in the domain of f. That's just the mathematical definition for an absolute maximum or minimum, and it's exactly what you think they should be. There's also what are called local extrema, or places where there's a point that's more extreme than its neighbors, but not of everything in the domain. So these are often called like a local maximum or a local minimum. So a local maximum of a function is f of c if f of c is greater than or equal to f of x for all x in a neighborhood of c. And a local minimum is a minimum for all x in a neighborhood of c. So what we mean by neighborhood is you're able to draw some sort of interval around the point, and inside that interval, that point has the maximum value. Now this interval has to include values both smaller and bigger than c. So it's those little tiny peaks or troughs that you see in a graph, but aren't necessarily the absolute largest peak or trough that you see in the graph. So it's not too hard to find examples of functions that don't have a minimum or a maximum. So for example, e to the x, that doesn't have any local extrema or any absolute extrema. There is no smallest value and there is no largest value. Other ones like sine of x, those have infinitely many extrema, because sine peaks at 1 every single 2 pi, and it has a minimum at -1 every 2 pi. And so because its domain is all real numbers, it's going to have infinitely many maximums and minimums. So if we're trying to find some extrema, there are 4 different situations where they might occur. So the first one is if there are boundaries of our domain. So you might have some extrema there. Any place there's a discontinuity, there might be an extrema. Anywhere where the derivative of the function is 0, and anywhere where the derivative of the function does not exist. These are the 4 situations that we would have to look to try and check if we have any different extrema. So, for example, if we were to look at this function, if we're looking for extrema at the boundaries, this one has a maximum value at point and a minimum value at the other endpoint. So if there are endpoints of our domain, those are places we would have to check to see if there are any extrema there. Other functions would be like e to the x on the domain 0 to 5. Now, we earlier said that e to the x doesn't have extrema. That's on the domain of all real numbers. This domain has endpoints. So because this domain has endpoints, we have to check those to see if there are extrema. And in this case, it does have extrema there. And then x squared on 1 to 3, that also will have extrema. Notice that these domains are the closed intervals, so that they include the endpoints. If they were open intervals, then those would not have extrema on the endpoints, because the endpoints wouldn't exist on those domains. We also could have extrema at discontinuities. So this function has extreme values at its discontinuities, and so that's something that we would need to check. We can also have when the derivative is 0, so anywhere where the tangent line is horizontal. So all of these places, the tangent line is horizontal, and so at all of these places we have local extrema. We have local minimums and local maximums. And then other places are where the derivative doesn't exist, so cusps or corners, so these 2 points right there, those are where the derivative doesn't exist. We can't calculate the derivative at that point, and those places are potentially where we might have some extrema. So as we just saw, local extrema can occur where the derivative of the function is either 0 or where it does not exist, and these are called critical points. So if you take the derivative of the function and you calculate all the places where the derivative is 0 or where the derivative does not exist, these are going to give us a set of critical points. Once we have those critical points, we can test it to see if it's a maximum or a minimum. The first derivative test is one way that we can test if a certain critical point is a local minimum or a local maximum. So the first derivative test says, if c is a critical point of the differentiable function f of x, then for a less than c less than b, with a and b sufficiently close to c, then if f prime of a is greater than 0 and f prime of b is less than 0, then f of c is a maximum. That means if the function is increasing before c and then decreasing after c, it's a maximum. If f prime of a is less than 0 and f prime of b is greater than 0, then f of c is a minimum. So if it's decreasing before c and then increasing after c, at c we have a minimum. If it's neither of the above, then f of c is neither a maximum nor a minimum. So this is a potential problem, and this is something that can happen at, for example, 0 in x cubed. At that point, it's a critical point, but it increases before and increases after, and so it's not a maximum nor a minimum. Let's go through an example. Let's find all local extrema of the function x to the fourth minus 4x cubed plus 4x squared plus 7. The first thing we would need to do is check, are there endpoints? Nope, so that's not going to be a situation. And so there aren't going to be any discontinuities because this is a continuous function. So our only two places we have to check are our critical points. So let's find anywhere where the derivative is equal to 0. When we take the derivative, we are able to get it as f prime of x is 4x cubed minus 12x squared plus 8x, which factors as 4x times x minus 1 times x minus 2. This has zeros at 0, 1, and 2, so those are going to be our critical points. So if we check each of these, we are going to figure out what f prime of x is between these different critical points, and then we're able to do that to determine if they are minimums or maximums. The way I do this is I approach it on a number line. So if we draw our number line, we are then going to be testing our critical points, and the way we do that is we test values that are on each side of the critical point. Something smaller than 0, so we're going to use -1. Something between 0 and 1, so we're going to use 1/2. Something between 1 and 2, we're going to use 1.5. And then something bigger than 2, we're going to use 3. So if we test each of these points, we're going to need to know what is f prime of -1, f prime of 1/2, f prime of 1.5, and f prime of 3. If we go through each of these one at a time, we find that f prime of -1 is -24, f prime of 1/2 is 1.5, f prime of 1.5 is -1.5, and f prime of 3 is +24. And so what we can do is we can say, well, at -24, it's decreasing, then increasing, then decreasing, then increasing. We only care about the sign. It's useful to know the numbers, but all we technically care about is the sign. So it goes negative, positive, negative, positive. So because it goes negative, positive at 0, that's going to be a minimum. Positive, negative at 1 makes it a maximum, and then negative, positive at 2 makes it a minimum. That's how I use a number line sort of diagram to help me figure out if they are maximums or minimums. And so we know we have a local maximum at 1 f of 1, so 1, 8, and then we have local minimums at 0 f of 0 and 2 f of 2, which both have a y value of 7. We can also use what's called the second derivative test. And so if we have a critical point on a twice differentiable function, meaning we're able to take two derivatives, then if f double prime at c is less than 0, it's a maximum. If f double prime of c is greater than 0, it's a minimum. And if f double prime of c is equal to 0, then this test didn't tell us if it was a maximum or a minimum. So if we go back to our example again, and we're trying to find all local extrema of the function, we first need to find the critical points, but since we already did that, we know it's 0, 1, and 2. We can then test f double prime of x at these different points. So f double prime of x is 12x squared minus 24x plus 8. So f double prime of 0 is 8, which is positive, so it's a local minimum. At f double prime of 1, that's -4, so that's going to be a local maximum. And then f double prime of 2 is 8, which is going to be a local minimum. And so that's how we're able to go through and use the second derivative test to figure out if they are maximums or minimums. I hope this video was helpful in understanding maximums and minimums and how we can use derivatives to help us do that. Please check out some of my other videos, and please like and subscribe if you haven't already, so that I can continue to make these videos. Have a great rest of your day, and good luck with the rest of your math.